So, how do we really know if a new drug is saving lives or if a new policy is actually working? How can we be 100% sure that one thing truly causes another and it's not just some random coincidence? Let's get into it, because figuring this out is one of the biggest challenges in all of science and honestly in life itself. And really, it all boils down to this. This great quote from the statistician George Box just hits the nail on the head. To understand cause and effect, you can't just sit back and watch. You have to get in there. You have to actually interfere with the system. You have to do something.
And to really get a grip on why this is so tricky, we're going to travel back in time, right to a president's deathbed where a common treatment might have been a deadly mistake.
Just try to picture this. It's 1799. George Washington wakes up with a terrible sore throat. His doctors, who are the best of the best, do what they think is right. They use the most advanced medical procedure of the day, bloodletting. They drain him of a shocking amount of blood, maybe half his body's total volume, thinking it would cure him. He was dead by the next day.
So, here's the million-dollar question. Did the treatment, the bloodletting, actually kill him? For literally thousands of years, doctors swore by this procedure. So, was it the cure that was the problem? Or would he have died from the infection anyway? How could we possibly know for sure?
Okay, so here's where it gets tricky. On the left, you've got the world we actually saw, the real world. Washington was bled, and he died. Simple enough. But to know if the bleeding caused his death, we have to compare it to this other world, this alternative world on the right, a world where he wasn't bled. And what happened there? Well, we have no idea. We can't see it. It's a total question mark. And this, right here, is what scientists call the fundamental problem of causal inference. It's this incredibly frustrating but also fascinating puzzle. For any one person, any single event, you only get to see one outcome. That what-if world, what they call the counterfactual, it's gone forever.
So, if we can't peek into that alternative world for a single person, how in the world do we solve this? Well, it turns out the solution is incredibly elegant, super powerful, and it all comes down to something as simple as the magic of a coin flip. Let's fast forward to a much more recent crisis, the Ebola outbreak. Scientists had two promising drugs, but they had no idea which one was better, so they ran something called the Palm trial. And they didn't try to guess who should get which drug. No, they just used a random device. Think of it as a high-tech coin flip to decide for each patient. And you know what? Because they were in a state of true uncertainty, this was actually the fairest thing they could do.
And here's where the magic happens. This is the genius of randomization. When you flip a coin, you're not just balancing out the stuff you can see, like a person's age or gender. The laws of probability mean you're also, on average, balancing out everything you can't see, their genetics, their diet, their immune system, stuff we don't even know how to measure yet. It's basically a statistical miracle.
And boom, look at the results. The bar chart makes it crystal clear. Because the two groups of patients were nearly identical in every single way except for the drug they got, that huge difference in survival rates, well, you can be pretty darn sure it's because of the drug. The answer was right there. One drug was clearly saving more lives. Randomization gave us an answer we couldn't get for bloodletting in 2,000 years.
I love this way of thinking about it. A single coin flip is a gamble. You have no idea what's going to happen. But when you have hundreds of patients, hundreds of coin flips, you're not the gambler anymore. You're the casino. And the casino knows that over time, the randomness cancels out, and the true average always wins. The real effect shows itself.
So the big takeaway here is pretty profound. The key to solving this huge life-or-death medical problem wasn't some new biological discovery. It was just the smart application of probability theory. It was literally a roll of the dice. Okay, so randomized trials are amazing. They're the gold standard. But what do you do when you just can't run one? The real world is messy, and a lot of the time, we have to find another way to get to the truth. I mean, this is the classic example, right? You can't just grab a bunch of people and say, okay, you guys are going to smoke a pack a day for 40 years, and you guys aren't. That would be completely unethical, not to mention impossible. So we're stuck observing the choices people make for themselves. And that, well, that creates a huge problem. See, the problem is that people who choose to smoke are already different from people who don't, right from the start. You can see it in these charts. On average, smokers and non-smokers have different ages, different incomes, different education levels. So if you just compare them, you're not comparing apples to apples.
So, to deal with this mess, statisticians came up with a really brilliant tool called the propensity score. All it is, really, is a single number that sums up the probability, the likelihood, that a person would choose to smoke based on all their other characteristics, like age, income, education, and so on. And when you actually plot out those probabilities, whoa, look at that gap. The smokers on the left were just way more likely to become smokers than the non-smokers on the right. This just proves what we already suspected. The two groups are not playing on a level field. They're not comparable.
So what do? How do we take this lopsided real-world data and force it into a fair comparison? Well, this is where a really cool statistical workaround comes in.
The method is called matching, and it's actually pretty simple to understand. First, you figure out that propensity score for absolutely everyone. Then, you take one smoker and you search through all the non-smokers to find their statistical twin, someone who had almost the exact same probability of becoming a smoker. You create a pair. You do that for all the smokers, and you just toss out anyone who doesn't have a good match.
And here's the payoff. After you do all that matching, look what happens to the groups. Suddenly, the box plots for age, income, and education look incredibly similar. It's like we've done statistical surgery. We took two totally different groups and carved out two new subgroups that look almost identical.
Here's the cool way to think about it. In your study, you have some coin people who had a high, maybe 50-50 chance of smoking. And you have die people who had a really low, maybe 1 in 6 chance. The original comparison was unfair because you were comparing a bunch of coin people to a bunch of die people. Matching just makes sure you only compare coin people to other coin people. And within that little matched group, it's pretty much random who ended up smoking.
And that's the whole point. This method of matching lets us take messy, biased, real-world data and force it to act like the clean, beautiful, randomized experiment we wish we could have done in the first place. It helps us turn noise into a clear signal.
So now let's go back to the outcome, the data on periodontal disease. The numbers are the same, but our confidence is totally different. Now that we've made the groups comparable, when we see this giant gap, we can be much more certain that it's actually caused by smoking, and it's not just a side effect of the groups being different to begin with.
So, from a president's final hours to the cutting edge of data science, we've seen how we can start to untangle one of the trickiest problems out there. We have these amazing tools, from random coin flips to clever statistical matching, that let us separate what's a real cause from what's just a coincidence. So the only question left is, now that we have the tools, where should we point them next?